Chapter 9, Section 2, Dot Product, Properties and Applications. In this section, we will dive into the properties and applications of dot product. These properties are foundational for understanding more advanced concepts in linear algebra, such as projections, orthogonality, and structure of vector spaces. First, let me briefly explain each property. Commutativity. The dot product of two vectors does not depend on their order. Swapping the vectors gives the same result. Distributivity. The dot product of a vector with the sum of two other vectors is equal to the sum of the dot products with each vector individually. Scalar multiplication. Scaling one of the vectors by a constant scales the dot product by the same constant. Non-negativity. The dot product of a vector with itself is always a non-negative value, and is zero only if the vector itself is the zero vector. Orthogonality. If the dot product of two vectors, u and v equals 0, the vectors are orthogonal. Now let's delve into each property one by one. Let's begin with the first key property, commutativity. This property is simple but essential to the structure of linear algebra. It can be written in this way. In other words, switching the order of the two vectors does not change the result of the dot product. Suppose we have two three-dimensional vectors, u and v. The dot product is computed in this way. And the dot product of v and u can be calculated in this way. Since scalar multiplication is commutative, that is, the product of ui and vi equals the product of vi and ui, the next important property of the dot product is distributivity. This means the dot product distributes over vector addition, and it is expressed in this way. Here, u, v, and w are vectors of the same dimension. What this tells us is that taking the dot product of a vector with a sum of vectors is the same as taking the sum of the dot products individually. If you write out the components and perform the multiplication and addition, you will see that both sides produce the same result. So, why is this property important? Because it relates directly to the broader concept of linearity. In the study of linear transformations and inner product spaces, distributivity is a foundational requirement. In machine learning, this property also ensures that operations like combining feature vectors or applying weighted sums behave in predictable and efficient ways. Next, let's talk about the property of scalar multiplication. This tells us how the dot product behaves when one of the vectors is multiplied by a scalar. It is written in this way. Here, she is a scalar, a real number, and u and v are vectors. The idea is that multiplying one vector by a scalar before taking the dot product is the same as taking the dot product first and then multiplying the results by the scalar. This is another reflection of the linearity of the dot product. Linearity means that the operation behaves predictably under addition and scalar multiplication. In machine learning and optimization, scalar vector operations are everywhere, whether it is adjusting parameters or applying learning rates. The fact that the dot product obeys this rule ensures that calculations are stable, interpretable, and efficient. Finally, let's talk about non-negativity and orthogonality. Let's begin with non-negativity. For any vector u, the dot product of the vector with itself can be written in this way. This result is always greater than or equal to 0. It equals 0 only when u is the zero vector, that is, when all components are 0. Now, let's consider orthogonality. If the dot product of two vectors u and v equals 0, the vectors are said to be orthogonal. Geometrically, this means the angle between the vectors is 90 degrees. They are perpendicular. This concept is central to practical methods like principal component analysis, PCA. In PCA, we project data onto mutually orthogonal axes in order to reduce dimensionality while preserving as much variance as possible. In short, the dot product enables us to quantify both the length and the directional relationship between vectors. Now, let's explore how the properties of the dot product connect to practical applications. We'll focus here on three main areas: measuring similarity, vector projection, and optimization algorithms. First, measuring similarity. Cosine similarity uses the dot product to quantify how closely two vectors point in the same direction. This concept is widely used in search engines, recommendation systems, and clustering algorithms. For example, if a user's preference vector is closely aligned with a product feature vector, that product is likely to be recommended. Next is vector projection. To project a vector u onto another vector v, we use dot product in this way. Projection is a fundamental operation behind principal component analysis and linear regression. In PCA, for instance, data is projected onto mutually orthogonal axes to reduce dimensionality while preserving structure. Finally, the dot product plays a role in optimization algorithms. In gradient descent, for example, the relationship between the gradient vector and the updated direction can be analyzed using dot products. If the gradient is orthogonal to the update, it indicates no progress is being made in minimizing the function. Let's wrap up. We explored four fundamental properties of the dot product: commutativity, distributivity, scalar multiplication, and non-negativity with orthogonality. These are not just technical details. They form the foundation of inner product spaces. We also look at how the dot product is applied in practice, from measuring similarity using cosine similarity, to extracting component via vector projection, to optimizing models with gradient descent. These applications show how the dot product bridges theory and real-world data science. In short, the dot product is not just a formula. It is a language for describing structure and a tool for extracting meaning. Thank you for watching. Please thumbs up and subscribe to my channel.